Okay.
All right. I'll pick up.
Awesome.
All right. So I'm Jacob. I work for a company called Neo4j, which is the commercial backer of a database called Neo4j, which I'll try and teach you guys about today. I have a bunch. I should have brought more because I would have gotten one for each of you, but I got a couple of these books from O'Reilly about graph databases. So since there's not that many of us today, like if anybody has any questions, just stop me and you'll get a book. So you gotta be quick with the questions because the books they'll run out. When the books run out, there's a little box of other swag which we already helped ourselves to. If there's other stuff inside the bag or box, please take as much as you want. That's just for your high enjoyment. So before I talk about Neo4j, I want to give a brief background on NoSQL in general and the movement of basically why did we end up reinventing databases? Like why did companies like Google and Amazon invest millions and millions and millions of dollars into replacing their legacy relational database systems, right? Because that's an interesting question to ask, and it's an interesting piece of background to have to understand why all these databases exist and what the purpose of them are. Like what were they built to solve, right? So you have this piece of technology, the relational database, that comes out of the 1960s. There was a big database war between relational databases and network databases and some other type of database I can't remember the name of. Relational comes out as the sole, like this is how you store data for various reasons. One of the main reasons being that it had a declarative query language. It had an algebra. The other databases, you would tell it what to do. You would say, please go to this record in the database and then scan in this way, do this thing. Like you could describe exactly what you wanted it to do. Whereas in SQL, you just say, please find me every user named Bob, and the database figures out what to do for you, right? So it's a much more compelling solution, and it remained a compelling solution for the last almost 50 years now. So what ends up happening, and I apologize for using this word, and I realize the irony since I am talking about NoSQL as well. It's not all going to be buzzwords, but this actually used to be a meaningful term, and it is kind of the clue to why NoSQL comes around. So Web 2.0 kind of meant a shift from Web 1.0, where people consumed information. You go to a website and you get information, right? Web 2.0, you would produce information. You interact with the website. It's the interactive web, right? And if you think about that for a second from the database backend's point of view, you're shifting the requirements of the database from having a couple of admins, a couple of content creators writing data every now and then. You know, you'd have maybe 10 users at the same time. Suddenly you have 10,000 or 100,000 users writing to the database. So you get incredibly write-heavy load. Yes. You also end up with generally ingesting much more messy data than you were dealing with before. Before in your relational database, you might have had, I don't know, the payroll for the company or like stuff where you could be in very, very fine-grained control over what the data looked like. But a user might not enter their email, or they might not keep the field within 128 characters. They might not, they create data where there's stuff missing and there's stuff that isn't all there, and you still want it. You want to be able to store it, and you end up with these very, very sparse relational tables where there's a bunch of nulls and a bunch of wasted space effectively, right? And you create a significant amount of this data. So to give you an idea of how high the write load is on the world's databases right now, so in the history of mankind, if you combine all of the information that we've stored up until 2 years ago, that is less information that was stored than that was stored in the last year. So the last year there was more information created and stored than in all of human history combined. Or to put it in another way, in the past 2 years, 90% of the information that exists in the world today was created, right? So you have a massive spike in data creation. And you have really, really interesting information, but you don't want to pay for relational databases to store it. You want huge systems like Cassandra and so on to handle this information. This is kind of what drives Google and Amazon to build new data systems where they're actually willing to give up stuff like ACID. They're willing to give up the idea that my data is going to be stored if the database has told me that it's stored. And instead they introduce the idea of eventual consistency, not because they want to, ACID is great, but because they kind of have to. They're like, we're willing to give that up if we can just handle this write load, right? So, with all this information, suddenly it becomes possible to start asking really, really interesting questions. You no longer have just a payroll, you might have a social graph from Facebook with stuff like, what do people like, what interests do people have? And suddenly you can stop asking questions like, what's the average salary in this room? And you can start asking questions like, given the interests and the likes of people in here, and my friends in here, who is most likely to buy me a beer? You can start asking much more interesting questions to your information, right? I'm going to skip this slide. This is actually a 45-minute talk, and I'm only supposed to talk for half an hour, so I'm going to skip a couple of slides. I'm not going to skip this one as well. But those are kind of the drivers of why these companies go off and build new databases. And you can kind of sum it up in this very unscientific formula of complexity, where you say that complexity is a combination of the size of the data you're trying to store, the semi-structure, the messiness of it, and how connected it is, right? And we think at Neo, because we build graph databases, that connections are some of the most important parts of your data. And these are, unfortunately, some of the things that relational databases are very bad at, because the most expensive operation that you can do in a relational database is a join. But suddenly when you have these social graphs, or you have these complex interconnected sets of data, you want to do lots of joins. You know, you want to ask, given these people and 15 friends out, what things do they like? What are the interconnections between the routers in my infrastructure? What are the interconnections between the data becomes very, very interesting, right? And it turns out the relational databases aren't that good at handling it.
Is the question?
Yes, I just want to go.
Yes, so they connect, that's not you said. So that's relations. Is that correct?
So you get into the semantics of relational databases, like why they're called relational, effectively. So a relation, different from a relationship, which I'll be talking about later. A relation in a relational database is a logical entity that may span multiple tables. But you effectively infer relationships using relations. So a relation, and I'm really poor at explaining this. So a relation, I think it's easier to talk about it as relationships. So you have, for instance, you would have two users, and the fact that they know one another, and the fact that they know one another is a relationship between them, right? That's the connection between them. Or you have, I don't know, you have two network routers, and they're connected by wire. That's the relationship between them. Or there's a dependency, or there's, and so on and so forth. Does that make sense?
Yeah, that's
kind of.
I never thought about those being two different things before.
I mean, because they're not really in a relational database, which is part of the beauty of the relational model in a way, that it's all just relations. But it makes a lot of sense when you start separating them, because you can ask semantically more easy to read queries, basically. You can reason about it in a different way if you separate the two. Now, I'll dig into that a little bit more in a bit. Right, so the classic way that we've dealt with the join problem, and something that most of the NoSQL databases, far from all of them, but most of the NoSQL databases do, is to say, well, performing this join on this very, very large table, or this long set of tables, is very, very expensive. We can't do it at runtime. We can't do it when a user hits the front page of the website. So we're going to denormalize. We're going to put it in memcache, or we're going to inline it into our relational tables, or we're going to do something that we get so that we don't have to do that join when the user comes around and does it, right? And the problem with that, as we all know, is that then you have to deal with invalidation. Suddenly the data exists in two places, and it becomes very, very hard to do real-time stuff, right? You want to do stuff that's based on things that happened 2 seconds ago. Like if you're doing recommendations, somebody's standing at the cashier in a store, and you want to print them a coupon. You want that coupon to be based on a recommendation of what they just bought. Looking at what they just purchased, you want to print them a coupon for something that's related to that, right? Can't do that if you normalize. But this becomes a very, very, very fast way of solving the problem, but it comes with a couple of drawbacks, right? We like to say that you separate between two basic approaches, and it says graph here, which I'm not super happy about because relational databases are on this side as well. But you effectively have aggregate-oriented databases, which make it very easy for you to work with aggregates and to kind of get around the join problem by denormalizing. such as document databases and column stores and so on. And then you have on the other side databases that, such as relational and graph databases, that say you shouldn't do that. You should store the data the way that you think of it, and the database should figure out the fast way to work with it for you. Right? You shouldn't have to do that manually. And now, yeah, I'm sorry about that. So, graphs. There's a bunch of graphs in the world, and as you've seen on your little reflection things that we're handing out, graphs are everywhere, right? The classic example is, of course, a social network, which we deal with a lot of social data and a lot of graphs today, and we'd like to deal with it more. It gives us a lot of interesting features that we can develop on it. It gives us a lot of cool new possibilities. So this is a graph of people knowing one another. You can't see the relationships, which kind of sucks, but in Neo parlance, these are nodes, the users, and they have relationships between one another, right? Another example, like I mentioned, is infrastructure. The internet backbone in Sweden right now uses Neo4j to basically map their network, and then they can do impact analysis. They can say if somebody cuts this cable, which universities are affected, which important civil services are affected, and so on and so forth. You can do really, really interesting impact analysis. Cisco uses this in their cloud hosting systems to basically say, if this thing goes down, which virtual services are affected by that, and so on, right? That's the graph. Geo stuff in general is super graphy. This is the tube map of Paris. Basically doing routing through this, right? What's the fastest way to get from this point to this point is a graph traversal problem, or it's a classic graph problem. Recommendations, like I mentioned, given that I just purchased a book, find other people that have purchased the same book, find books that they have purchased that I have not purchased, and recommend those for me to purchase. Basically find other people that like this kind of book that I just bought, and then recommend books that they've also purchased. Right? What is this? University LDAP, right. Authentication management in very large enterprises is usually incredibly complex. We have some of our biggest telco customers they have massive graphs of for their corporate customers, like given this administrator, which group is he a member of, which access rights does those groups grant, what types of access rights do they, do they travel further down, or does it just apply to the very, very complex graph problems, right? Parcel delivery, this is kind of similar to the tube map, but given a package, what's the fastest way to route it? The world's largest parcel delivery system uses Neo today to do real-time routing of the postal service, which is a great use case for a graph. This is what's it called? Actually, what's it called? Damn it, I don't remember. I'm going to skip this slide. So this is a graph of banks. Specifically, it's weighted by, as in the size of the nodes is controlled by how much of the bad debt they bought when the bubble burst in 2008. So you can see Merrill Lynch bought a significant amount of these really, really toxic credit default swaps. And you can use that to do basically impact analysis on the financial system. You can say, well, what banks are they connected to? What kind of ownership and loans do they have to other banks? And you can basically do estimates of what's the risk, what risk is this bank sitting at, right? Given that it's so closely connected to Merrill, very, very high risk, right? Overall, graphs are everywhere. There's a ton of graph problems in the world. Most interesting problems, I think, are graph problems. Which brings us back to Neo4j, which is a database that stores your data as graphs. It uses a graph model called the property graph, which was invented by Neotech about 10 years ago, and it's what most graph databases use today. It looks like this. It consists of nodes, like we've talked about, which aren't stored as giant blue boxes down at disk, but conceptually. Nodes have properties, so at this point you can kind of consider them documents in a document database, right? Just arbitrary JSON structures. They can have labels, which is a way to group the nodes into sets of nodes. And say these are persons. You can have topic nodes or whatever kind of node you want. Stick labels on them to group them into sets. And then they have relationships. Relationships have a type, and they also have properties. So in relational parlance, they're kind of like join tables. Every relationship in Neo has a direction, but if you don't care about the direction, you can just ignore it in your queries. There's no penalty for going in either direction. This is the whole model. It's pretty simple. Nodes can have self-relationships. They can have lots of relationships to the same nodes. They can have lots of relationships in both directions of different types. It's pretty much anything you can imagine doing with this. Unlike a lot of NoSQL databases, Neo is ACID compliant, which basically means that we don't mess around with durability. If we've told you that we're storing the data, that means the data's been flushed to disk and it's going to survive a crash, right? It also means all the other three letters in ACID, but it's an ACID compliant. It's an ACID compliant high performance modern database management system. It's specialized for connected data, like we talked about. Obviously, that's the whole thing. And so to give you an idea of what we mean when we say that it's optimized for that, if you imagine that you have a social data set, imagine that you're LinkedIn, and you want to do something like, given that a user is looking at a profile page, you want to tell them, you know this person through these people, this is the shortest path between you and this person, right? So if you do that, if you do that for 1,000 users, when we did this benchmark, I think we had an average degree of 50, so which means that the average user had 50 connections. It takes quite a while to do it in a relational database. This can be optimized down. The benchmark is a little bit old now, but you can get it down to something like 200 or 20 milliseconds. Neo does it very, very quickly by default, which is what it's supposed to be good at. But the interesting thing is that when you scale this up, so if you scale this up to 1 million users, you can imagine how, you're doing a recursive join on a table of 1 million users, and you're doing that at an arbitrary depth. It becomes a very, very expensive operation that's very, very driven by the total size of the data set. If you do the same thing in Neo4j, when Neo4j pulls out a single node, it immediately knows what relationships that node has, which means it never has to look at the whole data set. So if you imagine yourself doing this in the real world, what's the closest friendship between me and some guy in New York? Well, I don't ever have to care about, even if I include the data set of people in Great Britain or the data set of people anywhere else, like the shortest path between this person in New York and me is still going to be the same shortest path. I don't have to go to the London data set to figure that out. I just follow the shortest path, right? Using Dijkstra or something, which means that as you scale the data set up, the timing on Neo doesn't change. So this means that Neo ends up being very, very fast, even for very large data sets. This is called index-free adjacency, which is a technical term. In practice, it means that we don't have to use a global index to follow relationships, right? The graph is its own index. You can have indexes in Neo as well, which you generally use for, say, looking up a user by name or something like that. That's an excellent use for an index. You wouldn't want to traverse through the whole graph to figure that out. But when you found that user and you want to find other users like that user, or you want to find out the connections that that user has, then you get the benefits of index-free adjacency. So how do you use it? Well, let's say you want to describe a graph like this. Ben works for a company called Acme, and he's interested in these two topics, right? One way to draw that up programmatically is to draw it up in ASCII art. So if I clean that up a bit, you could draw it like this, right? And this is actually the concept that we built the query language around the idea of ASCII art patterns. To create the data that we were just looking at, you do something like this. I just realized it's using the old labeling system, which doesn't. Anyway, so we create 4 nodes. They're just JSON structures in terms of the query language. We create these 4 nodes, and then we say, well, they're going to be interconnected in this way. Ben works for Acme. He's interested in these 2 things. And then we ask the database to return Ben back to us. So this is the Neo4j equivalent of a SQL query to create a tiny little graph, right? If you do this for a bit, you end up with a nice little data set of users, companies they work for, and things they're interested in, right? And then we get into stuff like, well, given that I have this data set, how do I actually ask questions to it? Just like I described earlier, you would do something like an index lookup to find a user, and then you would traverse from there, right? So you would pick a starting point or lots of starting points, and then you'll traverse through the graph from there. So for instance, you could do pattern matching where you have a start point, and then you say, find me a pattern that looks like that, right? And the Neo4j query engine will write an efficient execution plan for figuring that out. And it'll run through the graph from the starting points that you told it to go through, and it'll find the patterns that you're interested in. For a lot of problems, you may not be interested in pattern matching per se. You may be interested in just traveling through the graph for various. I can't think of a use case for that now, which is ridiculous because there's lots of great use cases. Yes.
Edge weighting, is that supported correctly, or?
Yes, so you generally model it as a property on the relationship, and then you would take that into consideration when you write the query.
Okay, so it's not attached to the edge itself between two vertices as a known.
There's no like first-class citizen for weight, but generally like people do a lot of graph algorithms. Like they do the OpenStreetMap data set.
Traveling salesperson.
Exactly. So they do the OpenStreetMap data set. There's an OpenStreetMap backend for Neo where you can store. So they have the whole road network in Germany loaded into Neo, and then for each road is a relationship, and the distance of that road is a property on the relationship. And then you can run traveling salesman, or you can run routing applications on top of that.
I have a question.
Yes.
So Neo4j has just like it has nodes, right?
Yep.
And it's also using the graph searching.
Yep.
As like when relational database we have like the indexes and relations, different relations. So it's using the already the basic searches, like we have the binary search for graph searching and some other search techniques. So which one is it using?
So Neo itself doesn't bind you to any particular search algorithm. There's a lot of different approaches to how you move through the graph. I think so. It doesn't use binary search. Like if you ask the query language, for instance, find me, let's say find me the friends that you and I have in common, right? What it would do is it would recognize that I'm asking for a shortest path query, and then it would run a Dijkstra implementation.
So how would basically just traverse through the graph, or how would just find it? What's the mechanism or technique that it's going to use?
Underneath.
Yeah, I mean.
So underneath it would each node. So each node in each relationship is stored on disk. The relationships are stored as a linked list, and it basically like the relationships for each node is stored as a linked list. So it would pull out find your node ID, say, okay, find me all the relationships for you, and then pull out that linked list, go through it, find all the nodes that are connected to those relationships, and then it would repeat, right? But that's kind of the low level thing. Like it's basically traversing these data structures.
Yeah.
On the higher level, you can either use the Cypher query language. There's also programmatic APIs for writing more complex algorithms, and then you can choose yourself specifically what type of algorithm you can use, right? You can do, rather than doing a declarative query like you do in Cypher, you can do an imperative. Here's the programmatic thing exactly the way I want it to be executed. So it's very much up to you as a user.
And another thing, you just use the denormalized term. So like we use in relational database, we use the normalization and different techniques to normalize and remove duplication, something like this. So what's the difference between like denormalize and normalize?
So they're the opposite. So denormalize is when you do the wrong thing.
Yeah. A bit confusing.
So denormalize is so you want your data set normalized generally, because then you don't have duplication and you have a clean abstraction. And generally, the only reason why you would denormalize, basically like undoing all that work, is for performance reasons, because the normalized model is generally slow on relational databases to work with. So you denormalize. So it's the inverse.
Okay. And another thing, you said that relational databases don't have relationships, if I got it correct, if I heard it correctly from you.
They have relations, not relationships.
But then what's the one-to-many relationships? If I have just studied correctly in the books, many-to-many relationships, many-to-one relationships.
So conceptually, you can model relationships in a relational database. You can actually model it in any of the NoSQL databases. They're interchangeable, or any of the databases. You can model any model in it. And so in SQL, you would use a join table perhaps to do a many-to-many relationship. But in the actual relational algebra, ironically, there's no concept of a relationship. The whole thing is focused around relations, right? But you're totally right. You can do relationships in,
Yeah.
in a relational database. It's just generally not as fast as if you do it in a graph database, for the general case. So, traversing through the graph basically means you pick a starting point and you move through according to some specification, right? Rather than looking for a pattern, you say move through the graph in this way, return me the things that you want me to, or that I ask you to pick out. So, to do pattern matching, let's say that we want to do a basic recommendation. You want to say, find me colleagues that share my interests, right? And what we're basically looking for is the company that I work for, right? Other people that work in the same company, and then topics that we share in common, right? This is the pattern that we're looking for to do a basic recommendation, or to basically satisfy this query, right? Does that make sense? So just as we did before, you can describe this as ASCII art, right? Same graph. And you can write up a query for it. So what we do here, and if you want to dig more into Cypher and all the, I'm not going to talk about all the keywords and all the stuff that you can do with it, but what we're doing here is using Cypher's match keyword, which is basically saying, find me a pattern that looks like this. So to break it down a little bit, we say, find me a user with the name Jacob, me. We don't say explicitly start here, but Cypher's going to figure out that this is probably the best place to start because it's filtered down to just that name. And then we say, given me, find me topics that I'm interested in, the company I work for, other people interested in the same topic that also work for the same company, right? It's just the same pattern that we were just looking at. And then we do a little bit of, this is equivalent to the select clause in SQL, where we say, well, return the name of the colleague, count the number of topics we have in common, and collect all the names of the topics into each row, and you get a tabular result back just like you do in SQL. We ordered by the number of topics that we have in common, right? So it's a basic query. I highly recommend if you go to our website, you can pull it down, you get a nice little interface to play around with it. There's a couple of example data sets that comes with the database. And I'm going to skip these because I talked about use cases already, and just mention that it's available as a database server. You'll also hear it mentioned as an embedded database. That's how Neo started its name. That's or its life. That's where it's called 4j because it was originally an embedded Java database. Don't use the embedded database. Use the Neo4j server. It is licensed GPL in a community version, which means it's free software and it's free as in beer. You can use it in commercial projects just as you like. Just download it on our website. There's also an enterprise edition, which adds support for enterprise features like clustering and online backups and better management and monitoring tools, 24/7 support and all that stuff. It's AGPL licensed, which in practice means if you're open source, then it's again free as in beer. You can use it for commercial projects that are open source. If you're closed source, then we're also effectively closed source, and you need a commercial license from Neotech. That's kind of how it works. And yeah, it's at neo4j.org, which I shouldn't have said. It's at neo4j.com. We just launched a new website. I haven't had time to update the slides. So that's the thing. I'm going to try and do a really quick demo, and I'm very nervous because I haven't written PHP for almost 8 years. So I'm doing this for you guys. No less laugh. So we recently, and by we I mean me, built a little PDO driver for Neo4j. Let's see if I can make this bigger. Can you guys see this?
Yeah.
All right. What's it called? Composer.
That's right.
Composer in it, right?
Install.
Not install in it. No, in it. I wanted to do the thing.
Oh, okay, sure.
I'm creating a demo. Yep. I don't want a description. Doing all these things. This is awesome. I don't want to do that. What? No. Yep. So now I have a little composer file, right?
Yeah.
And oh wait, no, I'm not supposed to do this because it does the thing automatically. Composer. Require. See, this is helpful. It's kind of embarrassing that I'm supposed to demo this, and I'm just like, how do I do the next thing? All right, so composer require Neo4j PDO. And it says, give me a version. It's supposed to be master.
Good master.
Yeah, dash master. We haven't released a stable version yet. I'm very, very happy if you want to try it out. There's an issue tracker on GitHub, jakewins/neo4j-pdo. If you try it out, just let me know any issues that you hit. Right, so now I have in my composer file, JSON, neo4j-pdo, fine. And that means I also have a vendor file, right? So, oh wait. VI demo. Fine. So, PHP. And I say include, right?
Required, but include works.
What's the difference?
Required gets an error when it doesn't find the file.
Oh, that's way better. Let's use that. Require,
Then there's
vendor-
a waterload, not PHP.
Yep. And then we say something like connection to the database is Neo4j.
Neo4j.
Oh, right, it's not Python. Neo4j PDO. And then I give it a connection string to have a local database running in a little bit. Oh, so now we have a connection to the database, and we can do stuff like a basic query, say for each con query match, and so find me anything, any node, right? Return count. So return the number of nodes, right? Count, fine. As rows. So for every result, for every row in the result set, give me that back as row, and no, echo. Row count. Right. Does this make sense?
Yeah.
It should be pretty straightforward, I think. Even though it took me a little bit to do it. And then I need to launch a database really quickly. Give me 1 second. Maybe I already have one actually. Let's check. Yeah. This is the Neo4j admin interface, Cypher. So if we do this query that we're trying to do in PHP here, we should get a sensible result. Since there's 11 nodes. And then we do the same thing here. Oh, well, sorry, but well, there's an 11 there. You can see it. I forgot that new line. And yeah, that was a pretty lame demo, but at least that's how you use it. Yeah, give it a shot. And like I said, if you have any questions on the driver, please contact me. It's brand new. If you have any questions about Neo, I'll be here tonight. And otherwise, our office is right by Fervo. So if you come visit Fervo, I'll take you to the free coffee machine in the office, and we can discuss anything you like. Right. Are there any other questions?